So here this is the bridge rectifier, full wave rectifier. So we are applying the AC voltage and we are getting the DC at the output. So here you can see here we have the capacitor also, and here it's helping us to filter out the unwanted or pulsating or DC into pure DC. But at the same time, it's also helping us to improve the power factor. For example, let us say here now, this is the input voltage and bottom is the input current. So this is the problem right now we have. Because of the low power factors, you are getting more and more harmonics as well. So these harmonics are unwanted one in the output. So that will affect the output. You know the different order of the harmonics, second order, third order, fourth order, and so on. So we have the standard EN61000. This is the, for example, if you apply for the CE mark, you have to pass the standard for your product. Then only they will give you the CE mark. So this standard is giving us some values for each device, what is the allowed or permitted amount of harmonics. So this harmonics is also important, one of the important things when we talk about the power factor. So if you have the proper power factor, then you will have the proper relationship between the input voltage and input current. And here you can see the harmonic numbers, and they had also given the values, how many percentage it can be there. So of course the wanted one can be 100%, but other harmonics should be only very less. Just like when you drive the car, you can drive maximum from the speed limit, you can drive maybe up to 1 or 2% or 3%. If you drive more than that, then you will get penalty or problems, right? So similar to that, like the harmonics are also allowed in the circuit. You cannot avoid completely in some cases, but it has to be very, very minimal value, like 1%, 2%. So these numbers are defined by this standard. So when we talk about the onboard charger application, so this OBC, it's one of the current trend actually. So onboard charger application requirements are highly fragmented across the regions. So this is the onboard charger or OBC will have inside. So we will have the grid and we will have the filter and the PFC, power factor correction circuit, and we will have the primary DC to DC converter and secondary DC to DC converter, and we will have the filter to regulate the output, and finally the voltage will go to the battery to charge the battery. So this is the typical circuit, and this is, since this is getting more and more occupying the market nowadays, so this power factor correction circuit is also getting more and more important in the industry. So you can have this kind of for example, single phase power factor correction circuit or device that will help to improve the power factor in the entire circuit. It means it will not allow the current to lag from the voltage. It will keep the angle, the phase angle between current and voltage under control. So of course, there are so many applications. We have three-phase, single phase AC, or we have three-phase AC, or it can be a bidirectional or unidirectional, and how efficiency you want. And there are so many other requirements and cost and size and so on, because each application need a different size of the PFC also. So in the car, maybe you can use this kind of device, but if you use some other applications, you need a smaller PFC device. So it's really depending upon the application where you are using. So the system onboard charger has to cover many requirements. Yes. So if you have this kind of circuit design, there are several, you have to fulfill several requirements before you use this device in the application. And there are also various power classes from 3.6 kilowatts to 22 kilowatts. So you can see the description for each power level, and also you can see the adoption. Typical structure, just like this, just before what I showed in the previous slide. We have the rectifier, we have the power source, of course. you can use the transformer to step down or step up, or directly you can apply this one, and the rectifier is here, and the rectifier is giving the pulsating DC, and then we are using this power factor correction to correct the angle between voltage and current, and then we are using some kind of filter to to reduce the fluctuation in the output, because normally the DC output will be like this. If you use the full wave rectifier, this is a full wave bridge, so this is a pulsating, but we want the pure DC. This is the wanted one, this is the expected output, and this is the actual output. So we need to do something in the DC power supply. So, and also we have to, at the same time, we have to correct the power factor. So power factor, and then we are using the filter, and then we are using the regulator, and of course we have to use some kind of isolation circuits between them to provide the electrical isolation. And finally the voltage, the pure DC is given to the load, that is the pure DC. Pure DC is given to the load, so it's stored in terms of charges, electrical charges in the battery. It's based on the battery technology. So it's always better and good to maintain the power factor is greater than 0.1. So it means 0.9, 0.9 and 1. So the power factor, if you maintain this is the best. So you should not let the power factor go down less than this 0.9. The standard topology, there are two topologies we are using. We will see two topologies now. The one is called a totem pole topology. Another one is called, and it has its own advantages and disadvantages. For example, if you use the totem pole topology, then it fits all required power classes from 2.3 kilowatts up to 22 kilowatts. And also it has higher efficiency when using Coolmass technology for rectification. This is the totem pole. Totem pole, please take a look at the book, what is totem pole and how it works if you are interested. So this is providing higher efficiency, and it can be used in variety of applications from low power requirement to high power requirement, and it can be easily upgraded for bidirectional charging. So unidirectional or bidirectional, that is also important. And still it has also some disadvantages. For example, the cost is higher because it's using this Coolmass technology, and also it has a higher number of components inside. And the cost is high because the implementation technology is complex. So it means like you are integrating more and more components inside this circuit to design this, so it automatically increase the cost. And also it requires fast switching IGBTs. So then you have to use the correct rating of IGBTs. IGBTs are not cheap as well. So anyway, this technology has its own advantages and its own disadvantages. Another one is called the boost topology, not the totem pole. So boost topology has also its own advantages and disadvantages. So it can fit between 2.3 kilowatts to 22 kilowatts power requirement applications. And the cost optimized solution, if you want to go for a little bit cheaper solution, then you can go with the boost topology solution. And also it's a simple one. That is why the cost is reasonable. But the efficiency is not as high as the totem pole. So the efficiency is lower. So it means there are some losses in the rectifier. But here bidirectional implementation is not possible. So only the unidirectional. So when you go for a low cost, then you have to sacrifice the efficiency, and also you have to sacrifice the function. So here instead of bidirectional, you only have unidirectional. But in totem pole, it's the opposite. As we said just before, it's a little bit expensive, but it's providing higher efficiency